All right, here we are with this example where we want to evaluate this double integral from 0 to 2 and then 0 to square root 4 minus x squared of sine of x squared plus y squared dy dx. So, a couple things as we're taking a look at this. We can A, recognize that we've got some different equations here that look fairly circular. So things like we've got x squared plus y squared, we've got a square root of 4 minus x squared, which looks like a semicircle. So we might already be thinking polar coordinates. Another thing, though, that might help us move in that direction is taking a look at this integral here, sine of x squared plus y squared dy, or even if we tried to switch those to dx, dy, and do the dx first. Really, either way, we're going to run into this issue where we've got sine of an inside function where we've got like that x squared plus y squared on the inside. And if I think about trying to do u substitution there, let's say I do du where, let's say that I'm doing this with respect to y, since that's what's first. I would really have, well, x squared would go to 0. I would have 2y dy, and I don't have this y in there. So we've got this issue where the u substitution doesn't work because I don't have my derivative of the inside function as a product or as a factor in the integrand. So we can think about the fact that, well, when I do make that switch over to polar coordinates, we're going to get that extra fancy factor on the inside where we're going to have to do that r dr d theta. So let's think about switching to polar coordinates. Well, when we do this, we're going to have to think about how do we find what those r and theta bounds are going to be, right? We're going to try and switch this to an integral of sine of something, and then we're going to have r dr d theta. So first off, we have to figure out, well, two different things we have to figure out is what goes inside of sine and what are my bounds. Now we might be able to fairly quickly recognize what goes inside of sine, where x squared plus y squared just converts over to r squared. So that's nice. Thinking about the bounds with this one, we have to do an extra step that we haven't had to do in the other ones. In the other examples we've tried, the problem was already described to us geometrically, whereas this one is not. It's just given to us algebraically, right? We just have an integral that we have to interpret. So really what we need to do is we need to interpret what is R, what is that region. Well, taking a look at this, notice I've got, okay, y has these bounds. So we've got y goes from 0 to square root 4 minus x squared, which if we think about what that is, well, y equals 0 is the x-axis. And then y equals 4 minus x squared and a square root is an upper half semicircle with radius 2. So those are our two functions that we're taking a look at. Now we need to be careful though where we notice from here what my x bounds were was we had x went only from 0 to 2. So notice, right, we're going from this function here to this function, but then I only want to look at it from x goes from 0 to 2. So really, R is only in this first quadrant. We don't use the full upper half semicircle. We're only actually using a quarter circle in this instance. So now taking a look at that, what we can see is we can look for, well, what are our R bounds and theta bounds? Seems like R then goes from 0 over to 2. And then theta, notice I only need to swing through a quarter turn, so it's just going to be 0 to pi over 2. One thing that we can also recognize with this to find those R values is we can think about the fact that when I had this y equals 4 minus x squared in a square root, well, really that's y squared is 4 minus x squared. So we really got like an x squared plus y squared equals 4, which really looks like r squared equals 4 in polar coordinates. So it makes sense that we're using somehow an r equals 2 in this equation. But honestly, I think that just converting to the picture is the better way to go here when we're trying to take a look at that final, so trying to figure out those final bounds that we're looking for. So bringing those back over to our integral then, so r goes from 0 to 2, so that was our inner integral, and then theta goes from 0 to pi over 2 as our outer integral. And then we have to integrate. Luckily now when we take a look at this, notice again we see the compositions of functions, right? We have sine of r squared, so really there's a function inside of sine. So when we do think about that u substitution, now we'll have u equals r squared, and then thankfully du, we're going to get 2r dr, and we do have r dr now because we had to add in that r here. So we'll have 1/2 du is r dr. So all in all, this is going to be the integral from 0 to pi over 2 times the integral. We'll end up with sine of u, and then we'll really have times 1/2 du, and then this will still be d theta. Let's just switch those bounds over. So when r was 0 for our bounds, then u, which is r squared, is just going to be 0, and when r was 2, we'll end up with u is 2 squared, so 4. So we're going to end up with the integral from 0 to 4 of sine of u. So then integrating that guy, now it's just a sine function, so we'll have the integral 0 to pi over 2. We have that 1/2 there, so we'll really have 1/2 times the integral of sine is going to be that negative cosine of u, and then this whole thing goes from 0 to 4, and then we're going to go d theta. So then we're going to have the integral 0 to pi over 2. We'll have a negative cosine of 4 all over 2. Notice it's not a particularly nice trig evaluation, right? It's not one of our cosine values that's a reference angle. So we'll just leave it as cosine of 4, which is fine, and just treat it like a constant because it is. And then we'll subtract, plugging in 0, so we'll really subtract off negative 1/2 times cosine of 0, but cosine of 0 is 1. So really we'll end up with a plus from the double negative, 1/2. And this is all d theta. And then again, we actually recognize that nicely here, all of that is just a constant. So really we just have that whole thing, negative cosine 4 all over 2, all plus 1/2, will all just be times theta, where then that goes from 0 to pi over 2. And then we'll just evaluate those at theta. So we're going to end up with negative cosine of 4 all over 2 plus 1/2, that whole thing times pi over 2. And then we would subtract off plugging in the lower bound, but that would just be plugging in theta is 0, which makes the whole thing 0. So we end up with this constant as our final answer here. So again, in this one, we had to kind of pay attention that we recognized from the pieces of the integral, both from the integrand and from the bound on that inner bound, that we had these very circular looking functions. So the conversion to polar coordinates was going to simplify those expressions, but it also then added in that factor that allowed the integration to work easier. And then we also had to do this extra step where we had to interpret what that R region was. So we had to read off the bounds and draw the region and then refine the bounds in terms of polar coordinates in this example.